Hello, good morning to all. This side Avinash here. Today we are going to discuss about the topic understanding and managing chatter in machining. So what is chatter actually? So chatter in machining refers to a type of vibrations that occurs during the cutting process. This vibration is self-excited and result from the interactions between the cutting tool, the workpiece and the machine. Essentially, chatters happens when the tools vibrate resonate with the natural frequency of the machine or workpiece, leading to a feedback loop that amplify the vibrations. Chatter in machining arises from a complex interplay between the workpiece, tool assembly, and machine, which results in a distinct vibration signature for each applications. Analyzing machining dynamics enables a precise cause and effect understanding of these vibrations, which is essential for effectively mitigating chatter related issue. The first step in resolving chatter is identifying its root cause. Once these are understood, specific problems can be diagnosed and optimal process parameters can be established to maximize the machining efficiency and quality. While vibrations analysis has long been recognized as a valuable tool for addressing machining challenges, access to the necessary instruments and analytical capabilities has a traditional means limited. However, recent advancement in software and diagnostic services are revolutionizing this process. Modern solutions can automatically access vibrations profile for a specific machine tool holders, tool combinations, enabling the identification of optimal feed rate and spindle speed. These innovations empowers manufacturers to achieve superior performance, stability, and precision in the machining operations. So before moving forward, let's have a click that indicates about chatter in turning. Now we will move towards causes of chatter. So the first one is tool workpiece interactions. So let's have a look. During machining, the cutting tool engages with the workpiece, exerting force to remove materials. However, surface irregularities such as uneven material hardness, tool wears, or previous machining marks causes fluctuation in these forces. These variations lead to tool vibrations which can amplify over time and contribute to chatter. If not controlled, this instability can degrade surface finish, reduce tool life, and compromise dimensional accuracy. These factors just we have observed in the clip as well, that how the uneven surface or the regularities in surface gonna impact the tools. Apart from that, let's have a look about the second one, that is the cutting parameters. So the selection of the spindle speed, feed rate, and depth of cut significantly influences machine stability. Inappropriate combination of these parameters can inadvertently excite chatter. For example, high spindle speed may induce self-excited vibrations. Excessive depth of cut can increase cutting forces, make the tool more susceptible to instability. Improved feed rate may either amplify chatter or suppress it. It completely depends upon the tool's engagement with the workpiece. Now, the third one is the machine dynamics. So every machine components include the spindle, tool holders, and workable has inherent natural frequencies at which it vibrates most readily. If the vibration generated by the cutting forces or matches this natural frequency, like a condition known as resonance that we have observed in the chatter as well, the amplitude of vibration increases dramatically. This resonance amplified chatter potentially damage both the machine and the workpiece. Understanding the dynamic behavior of the machine structures helps in selecting operating conditions that avoid resonance. So, optimizing these cutting parameters, often through vibration analysis, helps in identifying the sweet spot where machining is both stable and efficient. Now, the next one is diagnosis of chatter. So, the first one we are having as a vibration analysis. So, what actually it is, let's have a look. So, vibration analysis is a crucial first step in identifying and resolving chatter in machining. This technique involves measuring and analyzing the vibrations generated during cutting to determine their source and characteristics. By understanding the frequency and amplitude of these vibrations, engineer can diagnose specific issues such as resonance, tool imbalance, or unstable cutting forces and adjust machining parameters accordingly. The insights gained from vibration analysis help optimize spindle speed, feed rate, and depth of cut, ensuring maximum efficiency, precision, and surface quality while minimizing tool wear and machine damage. Now, the next one we are having as a advanced software and services. As we know, like a recent advancement in machining technology have led to the development of intelligent software and diagnostic services that automatically analyze vibrations profile. These tools assess the dynamic behavior of a specific machine, tool holder, tool combinations, identifying the optimal operating conditions, often referred to as the sweet spot. By adjusting feed and speed based on the real-time data, manufacturer can significantly reduce chatter, improve tool life, and enhance overall machining performance. These automated solutions make high-level vibrations analysis accessible to workshop, eliminating the need for extensive manual calculation and expert interventions. Now, the question arises in our mind like what is sweet spot? So in machining, a sweet spot is the ideal cutting conditions that reduce vibrations, increase surface smoothness, and lengthen tool life. It is the point at where the cutting parameters like speed, feed, and depth of cut result in steady and efficient machining with little tool wear and chatter. So here we are having as a tap testing. So what actually it is indicating, let's have a look. A method where the tool response to a tap with a hammer is measured to determine its vibration profile. Okay, so this helps in identifying a stable operating speed and feeds. So let's have a look about how to identify sweet spot. So the first one we are having as a sensor placement. That means a small sensor known as accelerometer is going to be attached to the end of the cutting tool using a temporary adhesive such as wax. Next, we are having is an impulse testing. So the tool is lightly tapped with a specialized hammer equipped with a force sensor. This impact generates a vibrations response which is measured simultaneously by the hammer force, sensors, and the accelerometer on the tool. Now the next we are going for the frequency response function or RES analysis. So the recorded forces input and vibration outputs are combined to generate a frequency response functions which characterizes how the tools react to a different frequency of excitation. Next one or the last one we are having as a data analysis and stability predictions. So the measured data is processed using advanced software algorithm which analyzes the material properties, tool geometry, and cutting conditions. The software then identifies spindle speed that will result in stable cutting conditions that minimizes chatter and highlighting those that may lead to instability. This method enables manufacturer to fine-tune machining parameters, ensure optimal surface finish, prolong tool life, and enhance productivity while reducing the risk of a tool damage and machine wear. Now, the next one we are having as the machining system. So every machining system experiences vibrations during the machining process. However, it is essential to distinguish between beneficial and harmful vibrations. The quality and nature of these vibrations are influenced by factors such as cutting forces, the dynamic behavior of the machine tool, and the material property of the workpiece. So, in milling, time delayed surface regenerations differ from turning in that the surface waviness left behind by one tooth directly influences the cutting action of the subsequent tooth. So these interactions create a dynamic feedback loop that significantly impact machining stability. So let's just understood about the mechanism of surface regeneration. So first we will go for tooth to tooth interactions. So here we can see in the image as well, unlike turning, here surface effect accumulate from one revolution to the next. Milling involves multiple cutting edges. The wavy surface left by one tooth is engaged by the next, influencing chip thickness. Next, we are having as the feedback mechanism. The instantaneous chip thickness is determined by the both the tool current vibration and the previously machined surface. Since cutting forces depend on chip thickness, variation in chip load directly influences tool vibrations, creating a self-sustaining feedback loop. These vibrations cause relative displacement between the tool and the workpiece, leading to a waviness on the chip inner surface and the outer one. And the next one we are having as a stability and instability in the milling dynamics. So here you can see the left hand side of the image, the stable cutting. So when the vibration from one tooth is in phase with the surface waviness left behind, the cutting process remains stable, minimizing excessive variations in chip thickness and forces. Next we are having as unstable cutting. So if the vibration of subsequent teeth is out of the phase, chip thickness varies insignificantly, leading to unstable cutting forces and excessive tool deflection. So the thing is, the gain of the system influenced by factors such as chip width and cutting conditions dictates whether the process will be stable or prone to chatter. So understanding this dynamics relationship is essential for optimizing machining parameters and improve surface finish, tool life, and overall process stability. The additional part which I have added in this presentation is the good vibration versus bad vibration, which directly or indirectly is the stable cutting versus unstable cutting. So here we can see the various aspects which differentiate good vibration and bad vibration. So let's have a look. So the first one we are having as a cutting stability. That means in good vibrations we are getting stable and predictable cutting vibrations, whereas in bad vibrations we are having irregular and unpredictable cutting stability. Second one we are having is a surface finish, which indicates in good vibration like a smooth and consistent, whereas in bad vibrations it's like a poor with a visible chatter marks. Now the third one we are having is a tool wear. Like in good vibration, definitely just because of the stable and the smooth behavior, we are getting like a minimal and extended tool life. Whereas in bad vibrations, we are having as an accelerated wear and possible breakage. Next one we are having as a machining harmonics. So aligned with system dynamics, whereas in bad vibration, it is completely misaligned or causing instability. Next one we are having as a chip load. So how it is going to impact? So it like your chip pad is going to be completely even and controlled, whereas in bad vibration it is completely uneven and lead to increased vibrations. Next we are having as a regeneration effect. So definitely in good vibration there is no self amplifications or like a resonance which I can say, and in bad vibrations we are having as a waves on surface amplify or vibration that is going to be amplify the resonance of those vibration, and it is going to directly impact on the surface of the tool, right? So next we are having as an impact on workpiece. Like it's definitely like a precise high quality cuts, whereas in bad vibration defective parts, scrap or rework is going to be needed. And the last one we are having as a machine health. Then definitely in good vibrations it protects spindle's component, and in bad vibrations potential damage to spindle and bearing is going to be observed. Now we will discuss about the effect of chatter in machining. So the first one we are having as a poor surface finish. So in this, chatter leads to inconsistent cutting, resulting in a rough and uneven surface on the workpiece. So the second one we are having as a reduced accuracy. The vibration causes the tool to deviate from its intended cutting path, leads to a machining inaccuracies. So the third one is increased tool wear. Due to variable chip loads, erratic forces act on the tools, causing it to wear out faster than stable cutting condition. Now the next one we are having as a potential damage. So in severe cases, chatter can lead to damage of the workpiece and even affect the spindle of the machines, potentially lead to costly repairs. And the last one we are having as a cycle time. So chatter often requires reducing cutting speeds, leads to a longer cycle times. Now the next one is solution for chatters. The conventional approach to dealing with chatter is to stiffen the system with the shorter tools or dual contact tool holders with shrink or hydraulic fits and so on. So let's have a look about the various solutions that will help to reduce chatter. So the first one we are having as a adjust cutting parameter, which helps in finding the optimal combinations of speed, feed and depth of cuts. Secondly, we are having as a stiffen the system by using shorter or like a more rigid tooling setup. Thirdly, we are having as a vibration analysis, using the technology to analyze and adjusting the machining parameters for stability. And lastly, we are having as a by slowing down acceleration rate. Decreasing acceleration rate can reduce vibrations during the start and transition of a machine cycle on a different axis. Now, we will discuss about the key takeaways in vibration analysis. So vibration analysis is the critical tool for diagnosing machining issues and optimizing performance. It involves measures, analyzing and interpreting vibrations to identify potential problems and areas for improvement. Several fundamental principles form the basis of tap testing to determine the sweet spot in machining operations. So the first one we are having as a all machines vibrate, means every machines from household appliance to industrial CNC equipments inherently generate vibrations during operations, while techniques such as tool holding, work holding, and machine selections helps mitigate excessive vibrations. Understanding how these elements interact is essential for achieving stable cutting conditions. Next, we are having as a vibration is a symptom, not the problem. So vibration itself is not the root cause of machining instability. Rather, it is a symptom of underlying system behavior. When cutting conditions are stable, vibrations remain within acceptable limits. However, if system components are mismatched or improperly tuned, excessive vibrations can lead to chatter and machining inefficiency. And by analyzing the vibrations characteristics, make it possible to diagnose underlying issues. How? Let's have a look. So the first one we are having as the vibration signatures are unique. So every tool holder spindle machine's combination has a distinct vibration signatures, meaning that even minor changes in setup can alter the system dynamic behavior. Changes in cutting tools, tool holders or work holding setup can sometimes lead to changing the source of chatters, making it challenging to pinpoint stability issue. Recognizing unique vibrations pattern is crucial for unlocking a cutting tool's maximum performance potential. Lastly, we are having as the frequency analysis is essential. So as we know, like effective vibration analysis rely on frequency analysis, which breaks down complex vibration signals into their component frequencies. This process helps identify specific vibrations patterns, allowing engineers to direct instability, resonance point, and optimal cutting conditions for a given setup. Now, the next one is understanding vibration profiles. As we know, like machining stability is influenced by spindle speed, tool geometry, and cutting conditions. So stability lobes represent zones where chatter-free machining can be achieved across a range of spindle speed. By identifying these zones, manufacturer can optimize metal removal rates while maintaining process stability. So here are few key insights that I would like to highlight. So the First one are like you can see in the screen as well, stable and unstable region. The chart illustrates how machining stability varies with the spindle speed. Certain speed ranges allow stable cutting while other induces chatter. Effect of speed on a material removal. As the spindle speed increases, high material removal rates become possible. Additional chip load can often be increased without compromising stability. Now here we can see that all this thing or the vibration analysis is going to be done in the software called MSc Milmax software for the stability purpose. So here just have a look. So MSc Milmax provides advanced software tool to analyze and optimize machining performance. Let's have a look about the features and functionality. So here we can see in the left hand side of your screen the interactive dashboard, which includes an intuitive speedometer display stability zones, provide a visual representations of the tools with adjustable slider for axial and radial depth of cut, helps user experiment with the different cutting parameters to achieve the best possible material removal rate at a given speed. And here we are having as a tab test software, that is speedometer, which display color coded stability zones across the spindle speed range, where you can see like green color indicating the stable machining zone or like optimal cutting conditions, yellow indicating caution zones like a potential chatter risk, and the red one indicating unstable zone, which is highly likelihood of chatters, spindle stalling or tool breakage. That will automatically update an axial and radial depth of cut we are going to adjust it, right? So by leveraging MSc Minmax and stability law analysis, manufacturers can identify optimal machining parameters, minimizing chatter, and maximize productivity in high-speed mill operations. Now the next one is achieving remarkable improvements in productivity. Vibration analysis is not just about making small process refinements. It enables multiple fold improvements in machining efficiency, quality, and cost effectiveness. By identifying optimal machining parameters, manufacturer can significantly enhance productivity while reducing cyclic times and tool wears. So let's have a case study about an aerospace and high-tech tool manufacturer. So an aerospace tool manufacturing faced severe chatter issue while milling 3003 aluminum with an indexable cutter. Despite following the tool manufacturer recommended cutting parameter, by conducting a tap test and analyzing the machine tool holder tool vibrations profile, they achieved 3 times increase in metal removal rate, 80% reduction in cyclic time, 410% overall productivity improvement, enhanced surface finish and extended tool life, elimination of alcohol-based coolant mist, saving $25 per part. So the benefit of vibrations-based optimization extend across multiple industries, including aerospace, automotive, medicals, defense, and job shop. The average improvement seen includes 200% increase in feed rates, 300% increase in metal removal rates, 50% decrease in cycle time, and 100 hours of additional annual machining capacity per successful test. So by leveraging vibration analysis, manufacturer can unlock unprecedented machining efficiency, improving competitiveness while reducing operational cost. Now the next one is the best application. So let's just explore this part. So while tab testing every tool machine combination in a shop is impractical, focusing on high impact applications can maximize efficiency and productivity. By prioritizing tools and operations that are most prone to chatters, manufacturers can achieve significantly gain with minimal testing efforts. Tools with high length to width ratio are more susceptible to vibrations and chatter, make them ideal candidates for tab testing. Machinists can often identify the most problematic cuts based on the experiences, ensuring testing efforts yields the highest return. Many shops already use a limited common set of tools for roughing, make it easier to optimize cutting parameters. Performing tab tests on just a few selected tools allow for the creations of comprehensive dashboard that cover most roughing tool paths, improving efficiency across multiple operations. Even if this approach means occasionally using a suboptimal tools, the overall gain in metal removal rates and process stability outweigh the minor trade-off. A large job shop specializing in fault tooling system and precision component conduct a structure tab testing initiative. In this, 78 tab tests performed across 13 machining centers using 6 different tools, achieving 30% improvement in metal removal rates and tool life, and increased feed rates and speed by 30% across various common materials. So here you can see that by strategically applying tab testing, shops can standardize processes. Now, the next one is making testing practical. Decades of research have demonstrated the effectiveness of vibration analysis in optimizing machining parameters. However, widespread adoption has been hindered by the challenges of translating lab-based technology into real-world shape environment. While tab testing itself is a straightforward, but then also most shop lacks the necessary instrument and user-friendly analysis software has only recently become widely accessible. So one of them is MSc MillMax. So recognizing the need for a practical implementation, the US Department of Energy's Oak Ridge National Laboratory partnered with MSc Industrial Supply Corporations in December 2019. However, a 2 year cooperation research and development agreement is going to be made in between them. So ORNL trained MSc employees in tab testing, also known as impact testing or machining dynamic testing, to accurately assess CNC milling machining and machining centers. A nationwide team of MSc metalworking specialists has deployed to maintain shop of all sizes to conduct these tests and optimize exciting machining and processes. By 2021, MSc officially launched the MillMax services, bringing vibration-based machining optimizations to manufacturers across various industries. By integrating tab testing into shop environment, MSc MillMax enable manufacturers to enhance machining performance without requiring new equipments, reduce cycle time and tool wear through optimized cutting parameters, and increase material removal rates while machining stability and precision. The MSc MillMax services provide a major step forward in making advanced machining optimization accessible and practical for machine shop of all sizes. At the end, I would like to mention that the key to chatter control is understanding its cause, not just its effect. Thank you.